Hi, welcome to differential equations. Today topic is going to be continuation of our discussion on direction fields. We are going to have examples and we're going to talk about the software that we are going to use. So I'm going to start with some simple reminder of what the whole issue was, then talk about the software, and then we are going to have several examples here and try to uh, the best we can, we try to do these things by hand and then try to make use of the software as well. Okay, so before we get started, what was the topic? Let me just remind you that when you have a differential equation, ordinary differential equation, first order, it looks like uh, dy dx, the derivative, is some function of x and y, and this is some formula that were given to us on the right hand side. And the question is draw the direction field, or discuss something, draw the direction field. So that's a general topic for this section. Let's start with something very simple so we don't get overwhelmed with the details. So suppose we have dy dx is equal to y minus 2. We want to draw the direction field for this. If we say the direction field is a picture that takes a look at the xy plane, and then it asks what is the slope of our solution at any given point. Well, what is the slope? Slope is dy dx, and the differential equation gives us the formula in terms of our location. So if I am on this xy plane and I am asking what is the direction field or the slope at, say, a point coordinate, say 1 1. So x is 1, y is 1. I come here, so x is not used here, but y is 1. 1 minus 2 is minus 1. So that means I am going to be traveling at a slope of minus 1. Slope of minus 1 means headed toward lower grounds with the slope minus 1, going at minus 45 degrees. Well, what if I was at this point where the coordinates are 1 and say 2? X is in 1 and say let's make it 1 and 3. Well, again, is the y value that's used here, 3 minus 2 is going to be 1. We know that at that point slope is plus 1, so I'll be pointing upward. What about some point in between? Well, in between would be 2. So this is a point with coordinate of 1 and 2. If I put the 2 in my formula here, I see that my slope becomes 0. Means if I were here, my slope would be 0, which means my direction is horizontal. Well, we get the sense that if I go down here, y becomes negative, like 0, negative 1, negative 2, negative 3. These slopes become large negative numbers. It means I'll be pointing down at even steeper rate. If I am up here, if y is going through, say, 2, 3, 4, 5, and so on, the difference is going to be some positive number that's increasing. It indicates to me that these arrows become more and more steep. How about in between? If y is equal to 2, if y is equal to 2, well, the slope is always 0. We called that equilibrium solution last time. We said that we have this equilibrium solution y equal to 2, and then we get the sense that if we start at some point above this equilibrium solution, the solution is going to try to escape away, and as it escapes, its slope becomes higher and higher, so it's going to behave like this. If I start below this equilibrium solution, the slope becomes more and more negative as I move to the right, and the solution is going to start to go down, and that's how it's going to look like. Now if I had started some other spot on the page, similar thing would have happened, that I escape this way, and down here if I'm below 2, I'm going to escape down again. Then we had a name for this kind of a pattern. As you see, as we are going to the right, our curves move away from the equilibrium solution and they run away. We had a name for this. We call that the repeller, and so on. The opposite thing it would have happened if I had dy dx is equal to, say, 2 minus y. 2 minus y, it has the same equilibrium solution as before. So say 1 and 2, here's the equilibrium solution. Now if I'm above this line, say if I'm coordinate 3, say suppose this point is point with coordinate 3, put a 3 here, I get a negative, means at this point I am headed down because my slope is -1. However, if I were at y equal to, say this is 1, this is 3, if y is equal to 1, the difference becomes +1 and I'm headed up. As I go up, I come close to this line, the difference becomes a small number, and I'm going to lose steam, I'm going to lose the slope, I become more and more flat. We said it's like an airplane that's kind of reaching its cruising altitude. If I'm above, my slope is negative. As I come down, my slope is still negative, but in absolute value it's getting smaller, so I'm becoming flat. As I go forward, I kind of come close to this line, kind of like an airplane that is descending to the runway but never having a touchdown. So it's coming down like this, and this one is going up like that. Okay, this behavior, we call that stable. This was a stable equilibrium as opposed to this one that was called unstable equilibrium. These are both equilibrium solutions, so it's still y equal to 2, but this one is like a magnet that is attracting everything to it as we go from left to right, and for that reason this is called an attractor. This is called an attractor, this is called a repellent, and then that's a repeller. Both of them are called equilibrium solutions, and another terminology we have is stable and unstable. Okay, here the example was very simple. Right hand side was a very simple thing. We could analyze the picture and say some major qualitative description of the solution without actually having the solution. We haven't as yet talked about how to actually find that yet. We are just talking about the property of a solution we haven't even found. Now the question we are facing today is, well, what if right hand side was a lot more complicated than just y plus or minus 3 and stuff like that? Well, you see in these examples, things are getting a little bit dicey. You have x squared minus y squared on the right hand side. It's not too bad, but it's not as easy as 2 minus y. It's a bit more complicated. This one, even a formula is not given. We are just having a picture, and the question is, just from this picture, what can you say about what the solution is going to look like? Like you have a description of a qualitative description of a right hand side, meaning you don't even have the differential equation, you just have some ballpark information about it, and then we want to discuss what the solution is going to look like. Here is a problem trying to answer these things with a concept called isoclines, of some little use there. We are going to talk about that in context of one example to see what we are going to do with that. And then some rather tricky question here at the end. We are going to talk about that one as well. So what's our main aid in all of these things in case right hand side becomes crowded and we don't have time for drawing all those lines and curves and so on? What do? We have a direction field software. There are many of them. So let me take you to the page that I am giving the description for these things, and so on your on your page you go and see that we have all this information, and we have the direction field software. So direction field software, you come to this page, and we talked about this example of fields last time. Now how about software itself? The most famous, cleanest, most capable free example, the free software that's out there is due to Dr. John C. Polking from Rice University. It runs on Java runtime environment. So that one needs to be installed first, and then so there's a link here, and then you go to DField and pplane page, and once you have done that, you come and just install this DField software, and it's going to be just a second, and you're going to be all done. There's another one also if you want to keep that for future use. There's a pplane software as well. So you can install this one. If you don't feel comfortable about installing it, you can go to a lot of example of simpler, more rudimentary versions of the same thing that is on a web page, and you can use any of them. So you have a choice of one that's going to run on your laptop, even offline, and then there is option 3 here. Any of these things are available to you. A more extensive one that requires a lot of download, you have to get your MATLAB, and then some other downloads you have to do, and we are going to put that aside for the moment. So I'm going to use this one. I'm going to use this DField, but again, if you couldn't manage to install it, or you didn't want to install something that you don't know on your laptop, then try any of these 4 and see which one you like. So without further ado, what happens if suppose I try to run this thing, DField. So I see lots of pages come on on my screen all of a sudden, 4 of them. This is just copyright statement and so on. So you read that. This other one, DField messages, if there are some error messages and such, you might want to take a look at that. Right now we don't have any use for that. This page is where we have our main input. Everything input comes here, much of it comes here, and then our output it comes on this page here. Now let's go ahead and explain the input. Input, this is the left side of the differential equation on this box, and right side on this part, on this one. In this case, the example that is written, x is considered a function of time t, and right hand side is written in terms of x and t, and then perhaps some parameters such as a and b here. Let's go and do a simple thing like the example I just talked about. We had y, or y prime, and right hand side was what was it? It was y minus 2, wasn't it? And our variable was called x. It could have been called anything. We don't have any parameters a or b here, so that's irrelevant to our problem. So here is y. The prime here is written so small it's very hard to see. So it has to be read as dy dx. And right hand side, you write some formula in terms of y and x and perhaps some numbers. Okay, once you write your differential equation, comes the question of where do you want to show the direction field. So this is the window. You can decide where the window is going to be. So for example, I might say the window starts at x equal to -5 and goes, for example, as far as 5, and y goes from -5 again to 5. So kind of a square window. After we have decided on what the differential equation is and on which window we want to graph it, we say graph phase plane. Graph phase plane. So graph phase plane. So you see these arrows. These are the arrows that we were just drawing a second ago. This is y equal to -2. We were drawing these arrows and then trying to see where everything fits. And in this case, here is the same page. You notice that the arrows above 2 are headed up, arrows below 2 are headed down. If you want to start the differential equation at some point, what does that mean at some point? Like y of 0, here's my 0, this is my x when x is equal to 0. Suppose y of 0 is taken to be 1. You go here, now we are doing hand entry, so it's going to be a little bit off, but good enough for us right now. That's that solution. If the input was given at 1 and it was still y was equal to 1 also, that would be my starting point. And here's another example, and here's another example. What if the input was when x 0, y is 3? So I would have been here. What if it was told us that when x is 0, y is 4? Or when x is 1, y is 3, and so on. Now, you notice there are two groups. One is headed up, one is headed down, and the line y equal 2 is in between. Now, it's going to be really hard to go and exactly click on that line. If your hand is a bit off from here, which is pretty much in almost all cases, our hand is going to be off from the line, but we try. You see, I tried to click on 2, but it was actually a little bit below 2, so this is being pulled down. That's the example of instability. You move away from it a little bit, and then you're going to escape. Now, what if you want to have exactly at 2, and your hand is shaking like mine and such? What would you do in that case? You come here, and you say, keyboard input. So instead of clicking, you come and give input here. For example, if I say x is 0 and y is 2, I'm forcing, so I'm cueing my handshake and say start from that particular point, and our expectation is that now when you do like that, this is going to go straight and it's not going to bend up or down. So let's try again. Now our pictures are a bit crowded, so in case you want to restart, you go back to your input page. So here's the input page. Let me redraw this thing. Let me redraw it. So redraw the direction field to clean everything up. And now 0, 2, I go graph it, and then you see if this line is visible to you. It is perfectly horizontal. That is our equilibrium solution, which in this case was unstable. Okay, so we have a software to help us in case we are struggling. Now, the deal is the following. We are going to take these problems as much as we can. We try to extract as much information as we can by just playing with it ourselves. And then at the end, we go and make use of the software and try to solve the problem. So as you do the homework exercises, it sometimes insists that you do it by yourself. sometimes it encourages you to use some software. So very first one, dy dx is equal to x squared minus y squared. Let's see what can we say about this thing without using our crutch. So I have dy dx, or y prime if we wish, it's the same as y prime. Our differential equation was x squared minus y squared. Is that right? Anything else? That's it. Okay, what is it we can tell about the behavior of this direction field without jumping the gun and going to the software? Well, one of the basic things we expect to say perhaps by ourselves is the solution going to go up or down? Okay, that's a very basic thing. Is the solution is increasing or decreasing? Is it going up? Is it going down? Like we had in the previous pictures, you remember we separated two categories of these. You remember here, it was obvious that up here, everything going up, and down here, everything going down. Below 2, you go down. Above 2, you go up. And 2 came from solving right hand side, y minus 2 equal to 0. And so here we say this being positive or negative, the break even is when it is 0. It is 0 when x squared minus y squared is 0. So this is a friendly equation, rather friendly equation. We can hope to do something with it. Well, of course, we can factor it. Factor it is easy. X plus y equal to 0. So either x minus y is 0 or x plus y is 0. So this one tells you that y is equal to x, and this one tells you y is equal to minus x. You could tell from the beginning x squared is equal to y squared, so they are either same or they are off by minus. So where are these two lines? Y equal to x, y equal to x, well that's a famous 45-degree line, which is y equal to x. Y equal to minus x, where is that? Well, that's a minus 45-degree line, goes opposite direction, y equal to minus x. What's the significance of these? The significance is that on these lines, when x and y are equal or are just off by sign, the difference of their squares will be 0. If it is 0, means the derivative is 0. Derivative 0 means the slope is horizontal. So I know if I were to draw an arrow on these lines, and those arrows would be all just horizontal. Our arrows always go from left to right, because by convention time goes from left to right. That's the only reason these are always drawn from left to right. That's the only reason. Okay, so so much for what happens right on the line. Right on the line, therefore I'm traveling horizontally. But the question is, how about this region or this region, these regions? How am I traveling? So what do you think? Suppose I pick a point up here. Am I going to be headed downward? Am I going to be going up, or what? That's the question. So let's try it out. If you are on the y-axis up here, well, your x is 0, your y is some number, therefore you are always headed downward. So at this point you are headed this way, and same. It doesn't matter if you're above or below the x-axis. It's the as you go down, this becomes even more steep. So I had to draw this thing more steep going down. Well, what if you're on the x-axis? Say I'm at point 1 or 2 or something, and y is 0. When I put that number in the right-hand side, say x is equal to 2, y is equal to 0, that's of course a positive number. So I am headed up. So in this case, like I'm headed up like this. I go further out. X is a bigger number. I'm headed up even more steep than before, and so on. On the left hand side, the same thing. I am headed up. We go further up. I'm headed up much more steep than before. So what does it look like from these few arrows that we have? It's not a complete picture. Is that once I enter this region, I'll be headed down. When I get to this red line, I'll be going flat. When I enter this region, I'm going to be pulled all the way to infinity. So it looks like as if I'm coming down, coming this way, and then I am pulling in this direction. More or less, that is our guess. And how about here? Well, it looks like I am coming here, going up, and then perhaps I'm headed in the other direction, and so on. Now the question is, how close is our drawing to the real thing? So let's go ahead and try. See, I have y prime. I'm supposed to have now x squared. When you see red on the right hand side, so if by mistake I'd written t squared, the software will complain by showing it in red, telling me I don't know what t is. T is not your variable. You said your variable is x, so it gives us a little bit of warning. So x squared minus, that is mathematically incorrect, minus what? You have to do that, and then when you type it correctly, meaningfully, then it doesn't show in red. Okay, for the time being, we leave the window as it is. We ask for the direction field, which is also same as the phase plane, and then of course it's hidden here. Let's see. So this is the new graph that we got, and to see where we are headed, let's start somewhere. Suppose I start at this location. I come here. You see that it is pulling down. This is the location that we said we are crossing y equal to x line. We are going horizontally at that location. It enters into this region and then pulls up and then goes to infinity in that fashion. If you want to draw a few more, be my guest. Pretty much all of them behave that way. What if we are down here, say x equal to 1, y equal to minus 1, what happens? That's the other horizontal crossing. Here I'm crossing, and notice that it pulls up, comes down, goes through this crossing, and again goes into that region. Here, what if I start at x equal to minus 4, y equal to 0? You see that we are getting that kind of a picture. So when you draw quite a few of them, then your eyes get used to the arrows, and then you can perhaps continue with your analysis of the problem. So again, try to do as much as you can by just inspecting your algebra. You can see what you can see by yourself, and then step 2 is to resort to the software that you have and see what happens. Okay, so the question, perhaps in a homework or something, they might ask you to start at a specific point and then say something about where the solution is going to be headed. Let's draw another one. dy dx is that particular right hand side. So I have dy, excuse me, dy dx, it was like exponential of minus 0.1 x y2 Okay, we have exponential mixed into our picture. Let's make sure we got this copied correctly. 0.1 xy2. Yes. Yeah. What can we say? Again, we could go onto the software, type it in, and get a sense about what the solution look like qualitatively. The software doesn't give us any formulas or anything like that. It just draws a picture of what the direction field looks like. Okay, so in this case, I have my x, y again. What do I remember from pre-calculus or calculus about exponential? Exponential of any number is always positive. So what that tells me is that all over this direction field, all arrows are pointing up. It never happens that anything will be pointing down. So if you see a choice that has an arrow headed down, you say, well, that cannot be. What else can be used to get some sense about this thing? Well, we remember from college algebra, exponential of 0 is what? Exponential of 0 is 1, of course. So if my x is 0 or if my y is 0, I'll be dealing with the exponential of 0. And in that case, all of them will have a slope of 1. What does that tell me? Well, if x is 0, it means I am on the y-axis. Means all over here, all the arrows are horizontal. Excuse me, I made a mistake, a strange mistake. Let me correct myself. What was my error? We just said the exponential of 0 is 1, and that means I'm going at 45 degrees. So all over here, by the way, this is an example of isocline. I don't need to check one by one what happens. All of them are going at 45 degrees. Exponential of 0 is 1 in all of them. Same way it so happens down here also I'm going at 45 degrees. So 45 degrees all over. That's almost the end of all the easy things. What else can we say? Well, here x and y are going to be positive. So x and y are positive. I have exponential of a negative number. So exponential of some negative number is always less than 1. Is that right? Exponential of a negative number is always less than 1. So what does that mean? It means our slope is less than 1. Here the arrows are going to be having angles smaller than 45 degrees. How about in quadrant 2? In quadrant 2, of course, x is negative, y is positive. So xy squared is negative, and with this negative it becomes positive, and exponential of a positive quantity is going to be larger than 1. So up here our slopes are more than 45 degrees. So here I'm pulling up, like this. Down here, same way, x negative, y is negative, but since y is being squared, I'm again having large slopes. Down here, same as that, x is positive, doesn't matter what y is, and here also we are going to have small slopes. So what will happen if you start at some location? It looks like we are going to pull all the way up and go to infinity. Now, when are we going to cross the y-axis and such? Let's go ahead and delegate that to this one. So I go ahead and right hand side of my equation is I think for e we have to use exponential here. So exponential of, let me see if I remember this correctly, 0.1 x times y squared. Okay, let's see if it is happy with this. So you see these are examples of the solutions. Detailed analysis of some of them could be a bit more complicated than what we get very quickly on this software. So this is how these solutions look like. That's the direction field for us. Again, if a particular x and y is given for us, we can always come to Window, choose keyboard input. If I have like x equal to say -1 and say y is equal to 3, want to know what happens to that particular solution, and I don't trust my hand to picking that particular point, I go ahead and do it this way. Of course, if the picture becomes crowded, I can always redraw. After redrawing, I can if I want to investigate some particular solution, I go ask for that solution. Standard question is, would a solution exceed a certain value, move to a certain region, and so on. These are standard engineering kind of question to figure out if something's going to happen or not. You want to know if your solution is in a particular region or not, and that's where those type of questions come from. Okay, what else do we have here? Next challenge. Suppose I'm given a differential equation, but the right hand side, instead of a formula, they have given us just a picture. So, well, now we are up against a bit of a challenge. That software doesn't accept a picture. Perhaps you make something with chat GPT that will do that, but right now we are going to be doing the job of chat. So the question is, if I have dy dx equal to some function, and they tell me some general properties of that function, but don't tell me the formula, do I have a hope of getting any information? Well, it all depends on what's on the right hand side. The devil is in details. So what about here? This, you remember last time we called these things autonomous differential equations. Autonomous differential equation, right hand side was missing the x. So that's a big relief. So one big thing not to worry about is that the right hand side doesn't depend on x. Now they have given us some general picture of what the right hand side looks like. Do we have a hope of telling what the direction field is going to look like? Let's go ahead and try that. So here is, so we have dy dx. We said this is the autonomous differential equation. Right hand side is just a function of y. And we are not even given that function. We are just shown some picture, and we are told that f looks like this. So this is y, this is now f of y. The question is, what does direction field look like? Okay. We started this lecture with a simple example of this thing. Let me just bring that up. We said if you had dy dx, simple autonomous equation, this is y minus 2. We said the whole thing revolves around The whole thing revolves around where the right hand side becomes 0. So let me first of all, suppose this is y, this is f of y. F of y is equal to y minus 2. So y minus 2 looks like this. So instead of this picture, I have this one. Now, what was the significant aspect of the direction field here? You said the significant aspect was the equilibrium solution. The equilibrium solution was when right hand side was 0, which means y is equal to 2. Where is that? That's just this point. Y is equal to 2. So the point where our picture crosses this axis here is this is a significant clue. How did this clue help us in getting the picture? The clue helped us by saying, okay, on the xy plane, now we are having a little bit of a issue with the fact that in these pictures y is typically drawn horizontal, and in the xy plane y is drawn vertical, but that's a minor thing. So y equal to 2 was the location of our equilibrium solution. So y equal to 2 was here. And then for y is larger than 2, we notice that our f is positive. F is positive means the right hand side is positive, means the derivative positive. It means we are being pulled up. So this positive here connects to the fact that this is increasing here. On the left of 2, like in this location, f is negative. Let me draw this in negative. And that means if y is less than 2, your slope is negative there, and negative, this negative refers to the fact that you are pulling down here. Okay, by analogy with that, we say that crucial events are these 3 points, wherever they happen to be. So suppose like this is at, say, 1, this is at -0.5, and say this is at -2, whatever they happen to be. You just eyeball it from the picture. And then what? Then, so okay, let's qualitatively draw this direction field. What do? We draw our x, y coordinates. These are going to go, so we have 1, say -0.5, and say -2. These are our equilibrium solutions. We draw them in red. Now what? Now we say, you notice this f's are positive. From -0.5 to 0.5, I have positive. What does positive right hand side mean? It means the slope is positive, which means I am increasing. So from -0.5 to 1, I am increasing. What about after 1? After 1, you see f is negative, so it means my solution is decreasing. How about between -0.5, -2? Over there also the solution is decreasing. How about to the left of -2? All over here, f is positive, it means I am increasing. Well, what does that tell me about the direction field. Close to these red lines, the equilibrium solution or solutions are going to become flat always. So I start flat close to this. I pull up, and then again I become close to that one. This one is coming from Neverland, from infinity it's coming down and then coming close to this line. This one is coming down. It has to start from close to this equilibrium solution and then has to be stopped by the other equilibrium solution. This one is increasing. It has to start from minus infinity and increase and come up here. So we could generally say what the solution looks like without even having the differential equation. Only a little bit of information about what the right hand side look like. So long as we know it's autonomous, we can tell what kind of a solution we have showing itself on the direction field. Of course, even this is an approximation because f itself was given to us in an approximation. Okay, so this was another example of how powerful direction fields are. So sometimes you can even say what the solution looks like without having full information on the differential equation itself. dy dx equal to x plus y, graph that using isoclines. Isoclines was a topic people used to use before there were any software, just to make their life a bit more bearable, because before the advent of computers, doing these things by hand was quite a task. This isoclines was a little bit of help in getting the work cut down a little bit and more tolerable. So let's see what was the idea there. So we have question dy dx is equal to x plus y. Question is draw the direction field but using isoclines. So with that software available to us, a bit hard to sell this, but let's try. What is the idea? Well, the idea is when you want to draw the direction field, you want to put the x and y values in this thing, get a slope, and draw your little line segment, as sometimes they call the lineal elements, those little arrows. You want to draw all of them. So if you get a grid and then you calculate x plus y on that grid, randomly going back and forth, you get all sorts of numbers, and drawing them one by one could be a bit tedious. So what do we do? So let's draw one type at a time. Like say, when x plus y is equal to 1, then the slope is 1. All of those little lineal elements, all of those little line segments, they're all at 45 degrees. Let's draw all of them at the same time. So I guess, say, let's look at the right-hand side being 1. And that's what an isocline is. All of those locations have the same inclination on the plane. So we go the following. We say, so where is this? Where is x plus y equal to 1? Well, we have learned this thing all the way back in algebra 1 or 2, whatever. Y equal to 1 minus x is a line. Let's say this is 1, say this is 1. X plus y equal to 1. That's just a line 1 minus x. It has an intercept 1, slope minus 1, and however you want to draw it. Let's draw it with a different color. This is x plus y equal to 1. That's an isocline. Right hand side all over all of these things is 1. Well, what does that mean? It means every point here, your slope of a little line segment is 45 degrees with respect to horizontal. All of them are going to look like little lines like this. So with one single stroke, you have plenty of the arrows of the page all drawn all at the same time. You don't need to go reinvent each one of these. Well, how about the rest of the page? Well, the rest of the page, you say, well, what if this was 2? X plus y equal to 2. Well, what is x plus y equal to 2? That's another straight line. So happens that we are all working with a straight line. This is x plus y equal to 2. Well, how about all of these? The element that you draw at every point of this line has to have a slope 2, so a little bit more steep than this one. So it's perhaps all of these at slope 2. So we get a sense that as we march from this third quadrant toward the first quadrant, our solution lines are going to go become steeper and go like this. Well, what happens here, for example? Here is what? Here is x plus y equal to 0. What about then? Well, 0 means the slope is 0. It means you are horizontal. All over here, your line elements are, so you quickly have all of these. Well, what about down here? Well, down here would have been x plus y is equal to minus 1. Well, what does minus 1 mean? Well, it means you are going at slope minus 1. Slope minus 1 would be exactly on this line itself. Well, how about another one? Suppose we have this one. This is x plus y equal to minus 2. So most problems here, they ask you minus 2, minus 1, 0, 1, 2, just to have some representation. At all of these points, you have a falling even faster than here, so something like the following maybe. So here I'm horizontal, here I'm coming down. So I get a figure like that. Now let's go ahead and verify which one of see what does the software tell us. Well, in this case, we have x plus y. We draw the phase plane. This is the phase plane. By the way, this is what we had. Pull this to the side. So this was coming down at 45 degrees. That is this line that is coming down here. Let me enter it here so that I'm not deviating the keyboard input. So that would be, for example, x equal to minus 1 and say y is equal to 0, x plus y. That's the horizontal line that I had drawn here. What about being above it? So the solution above it look like this, the solution below it look like this. So it's quite common that these are called the family of solutions. We have a family of solutions and they're like subfamilies. So we have a subfamily here that is pulling up to infinity, and then we have another subfamily here that's pulling down to minus infinity, and we have a solution that is kind of in between these two kind of solutions. finding these subfamilies in the differential equation is one of the basic type of questions. Right now we are just doing visually. We can see the various families that we have here. Okay, so that was the issue of the isoclines. What else do we have here listed up for us? Item number 5 is kind of a little bit of a tricky question. I will explain that shortly. So let me take a sip of water and come back. Okay, for the last item for today, we have a differential equation, and the question is what would happen in the long run in solutions that start in a certain specific place. So we have dy dx is equal to x times y minus 7 squared minus 2, and then at x equal to 0, whatever our solution is, we are assuming it to be less than 7. What's the significance of that? Now we are facing a question, is it true or false? In the solution, when we consider y of x, the solution, as x goes to infinity, would it be that y also goes to infinity? So I'm starting, I'm having differential equation. I'm starting at some point below 7. I asked the question, as x goes to infinity, would y go to infinity? What does that mean? X going to infinity means I am going toward the right. Question is, what does y do? Does y go up? Does it hover around somewhere in between? Does it go to minus infinity? So here is y going to plus infinity. Here y is going to minus infinity. And here perhaps hovering somewhere in between. But this is very different from the rest of question that we had here, and it is heavily dependent on what formula you have on the right hand side. So the idea is very specific to this problem. Well, let's just go ahead and do it and see what happens. Let's just go ahead and play a bit with this thing. For example, if y is equal to, if x is equal to 0, what happens to my solution? So if x is equal to 0, well, I have dy dx. All of this falls to 0, and dy dx is minus 2. So what I have here is a little bit of an isocline. All over this line, slope is minus 2. Okay, that's great. What else can we say? How does that relate to any of these things? Let's go ahead, choose a y surrounding this number 7. So what if I choose y is equal to 7? If I start with y equal to 7, my dy dx becomes, again, minus 2. And then what I understand from this is that on the line y equal to 7, suppose is y equal to 7, all over that one, my slope again is minus 2. I'm pointing downward. Lots of signals of things pointing downward. Going to infinity, well, you are not going to be pointing downward for sure, but how does that answer the following situation. Suppose I take y is equal to 6 at all points where y is equal to 6, dy dx, 6 minus 7 is minus 1 squared becomes plus 1, and now I have x minus 2. So at y equal to 6, so if this is 7, at 6, my slope starts at minus 2, for example, goes down. Eventually, if I go way out, when x is larger than 2, it becomes positive, and I break through this line. True enough, at the beginning I'm coming down, toward the end I'm going up. Well, let's try another one. Suppose I get y is equal to 8. Again, dy dx. 8 minus 7 is 1. It's going to be x minus 2 again. So we have the picture that, again, suppose this was 7, and now at 8, this is all points with coordinates y equal to 8. At the very beginning, my slope is negative, I'm falling. At the very end, I am positive, and when x is larger than 2, I am breaking through that line. So, what is the question here? The question is, in xy plane, if this is the point 7, if I start with starting point y0 below 7, would I, if I start from here, would I ever go to infinity? Can something like this happen? Can it go to plus infinity? Well, we know when we start, our slope is minus 2 anyway. We say slope all over this line. We know for sure when we are starting, we are coming down. Okay, we are starting downward. Well, the question is, if you start downward, would you ever have a chance of turning around and coming and becoming positive? Think about it for a second and see, can something like this happen to our picture? So again, we are starting with a negative value for so when x is 0, our slope is minus 2, and the question is, if he wants to go to plus infinity, well, he should turn around and become positive at some point to point back up, and the question is, does it have a chance to do that? So think about it for a second. So what do you think? So again, the question, if I start below 7, would I ever go to infinity? Well, the answer is no, and it has to do with what we noticed here and here. At 7, we know that direction field always pointing downward, and anytime you're on that line, you're supposed to go down. And here you start going down. If you want to go to plus infinity, you have to cross this line. That means at this point you have to be pointing to direction of going up. Well, that's going to be a contradiction, because we just said anytime you are on the line y equal to 7, you are pointing down. So line y equal to 7 acts like a repellent for all the approaches from below. It just pushes all of them going down. It's not allowed, none of them is allowed to cross through this barrier and go up. Okay, so once again, we're starting from below this line. We can never approach the line y equal to 7 because that line slope on that is negative. We are not allowed to cross it. We are always pushed to have a downward sloping curve on that line. So true or false, the answer is that this is false. It never happens. Now let's just go ahead and see how complicated this problem gets to be. Like when is it that we go to infinity and when is it we don't? So let me okay. On the right hand side we have a new function, x times y minus 7 to power of 2 minus 2. So we draw the face plane for this. It's pointing downward. So the question here is, well, let me go and adjust my window. The problem is asking us to investigate solutions that start below 7. So our window better include 7. So you see 7 is somewhere here. So let's look at some solution. If I at y0, let's say I start at 0, where does it go? It pulls itself up, but it levels down to a certain curve. It doesn't go to infinity. I start here again, start here, start at 7, still go up, start at 8. In fact, we are still not making it to infinity. Here we are not getting it. Now, somewhere here, somewhere above perhaps 9 or so, that's the first instance where the solutions start to go to plus infinity. To see the picture clearly, let's go ahead and increase our upper window. Let's go to say y equal to 20. I'll make everything 20. So 7 was, let's start at 5. You're still going horizontally. 7 is still pulling down. Now you see there is a location here. It's perhaps around 9.5 or something, where the solutions start pulling up toward the plus infinity. It was asking us if such an eventuality happens if I start down here. No, it doesn't. None of these solutions go to infinity. They all flatten out. You notice what happens to all of them? So there is this curve. They all get arrested by that curve. It's kind of a glass ceiling. They cannot make it pass through here. And that is, so a more advanced question here would be, where is this point where we have two families of solutions, one that converge to this curve on the right hand side and the other ones that go to plus infinity? What's the break point between these two classes? That would be an interesting project for some of you to work on. Okay, so what did we learn today? We learned benefits of the direction field. Notice that it's a tedious task to draw it. There are software that draw it for us, and they can be a very handy tool for us to explain what the solutions do. We learned also about autonomous differential equation, talked about that one, and equilibrium solutions, a little bit about isoclines, and that interesting problem at the very end. So until next time, good luck and God bless.